Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module we are discussing Structure of Selective Interhalogens and Sulphur Fluorides. In this module, interhalogen compounds, structure of IF7 iodine heptafluoride, structure of ClF3 chlorine trifluoride, structure of BrF5 bromine pentafluoride, structure of SF4 sulfur tetrafluoride, structure of SF6 sulfur hexafluoride, and problems based on these concepts. First of all, we are dealing with interhalogen compounds. What do you mean by an interhalogen compound? As the name indicates, these are the compounds formed by the combination of different kind of halogens. Interhalogen means within halogen. So, the compounds which are formed by the combination of two or more different type of halogens are termed as interhalogen compounds. These compounds are of different types. They exhibit different geometries and shape. The geometry, hybridization, their shape, etc. can be easily explained with the help of the principles of valence bond theory. Now we can enter into details of interhalogen compounds. Interhalogen compounds are molecules formed by the combination of two or more different halogens. Fluorine, chlorine, bromine, iodine, astatine and tennessine are the halogen family, out of which fluorine, chlorine, bromine and iodine are reactive halogens, and interhalogens are produced from these elements. The interhalogen compounds are formed when halogen group elements react with each other. In halogen group elements, we are generally excluding astatine and tennessine. All other elements may react together to produce interhalogen compounds. These interhalogen compounds are of four main types, or interhalogen compounds are of different categories. There are four types of interhalogen compounds. Such interhalogen compounds are AX type interhalogen compound. Typical examples include IBr, BRF, etc. The second category is AX3 type interhalogen compound. Example is ClF3, that is chlorine trifluoride, BRF3 bromine trifluoride, and ICl3 iodine trichloride. The third category of interhalogen compound is AX5 type. Typical example include bromine pentafluoride, BrF5, and iodine pentafluoride, IF5. The last category of interhalogen compound is AX7 type. The one and only molecule belongs to this category is iodine heptafluoride. Only one AX7 type interhalogen compound is known, that is iodine heptafluoride. This is because iodine is the biggest sized halogen among reactive halogens and fluorine is the one with the smallest size. So, iodine can extend its valency up to 7 to form iodine heptafluoride. Hybridization, geometry and shape of AX type interhalogens. The hybridization is sp3. That is, in AX type interhalogen, the central atom A depicts sp3 hybridization. This is similar to halogen diatomic molecules. The hybridization of sp3 with respect to the central atom A can be proved by taking the expression for finding out hybridization from the molecular formula. We know that expression, hybridization is equal to half into V plus or minus C plus A, where V represents the number of valence electron around the central atom, M represents monovalent atom, C represents cationic charge and A represents anionic charge. It should be noted that here the central atom is A. It is associated with the 7 valence electrons since it is a halogen. X is the one and only monovalent atom present there. Since it is having no charge, cationic charge as well as anionic charge is equal to 0. So, we can calculate the hybridization equal to half into 7 valence electron plus 1 monovalent atom. Cationic charge is 0, anionic charge is 0. So, this will be equal to 4, and hence it is clear that since the value is 4, 4 orbitals are take part in hybridization. So, we proved that the hybridization is sp3. Now, for sp3 hybridization, the geometry must be tetrahedral. but you have to keep the fact that in this molecule AX, the central atom A is directly bonded to only one halogen X. So, 3 lone pairs are present on the central atom A. If we are removing that 3 lone pairs, we will get a linear shape for this AX type interhalogen. Now we are discussing the hybridization geometry and the shape of AX3 type interhalogen. It is very well clear that the hybridization will be equal to sp3d. We can prove it by using the previous equation. Hybridization H is equal to V plus A minus A plus A divided by 2. Here the central atom A is having 7 valence electron and 3 monovalent X atoms are also present. So 7 plus 3 divided by 2, that is equal to 5. 5 orbitals are take part in a hybridization, that is nothing but sp3d hybridization. So we are anticipating the trigonal bipyramidal geometry, but in the trigonal bipyramidal arrangement you can have 5 corners and only 3 bond pairs are present in this molecule. As a result, the 2 positions will be occupied by the lone pair of electrons and the 2 lone pairs are present in the planar position. If you are removing that 2 lone pairs, you will get a shape that is nothing but T shape. So, it is very well clear that the AX3 type interhalogen depicts sp3d hybridization, trigonal bipyramidal geometry with the 2 positions occupied by lone pair, and excluding that lone pair, you will get a shape of T. Now we are dealing with hybridization, geometry and the shape of AX5 type interhalogens. Here it is clear that the hybridization will be sp3d2. This can again be proved by using the expression for finding out hybridization from the molecular formula, that is hybridization equal to half into V plus A minus E plus A. On substituting proper values, you know that the central atom A has 7 valence electron and here 5 monovalent atoms are present. So, 7 plus 5 is equal to 15 divided by 2, that is equal to 6. 6 orbitals are participated in sp3d2 hybridization. So, we invariably proved that the hybridization here is sp3d2 and hence the geometry will be octahedral. But it should be noted that there occur the presence of a lone pair on the central atom A, and if you are removing that lone pair, you will get a shape. That shape is nothing but square pyramidal shape. So, every AX5 type interhalogen compounds depict sp3d2 hybridization with octahedral geometry and square pyramidal shape. Finally, there is one more category of interhalogen compounds. They are nothing but AX7 type interhalogen. The hybridization geometry and shape of AX7 type of interhalogen compound is described here. Hybridization scheme represents sp3d3 hybridization. This can be proved by using the expression for hybridization. Here there are 7 valence electrons around the central atom A and 7 monovalent atoms. So, adding them together and divided by 2, you will get to 7. 7 orbitals are take part in a hybridization, that is nothing but sp3d2 hybridization. The one and only molecule belongs to this category AX7 shows sp3d3 hybridization, and the geometry of the molecule is pentagonal bipyramidal. Since there is no lone pair of electron around the central atom, it is clear that the geometry will be same as the shape of the molecule. Both are pentagonal bipyramidal. That all about hybridization, geometry and the shape of 4 different categories of interhalogen compounds. On a sum, we can say like this: AX type interhalogen shows sp3 hybridization, AX3 type interhalogen show sp3d hybridization, AX5 type interhalogen show sp3d2 hybridization, and finally AX7 type interhalogen depicts sp3d3 hybridization. Now we are taking structure of IF5. We are now exclusively discussing the structure of iodine heptafluoride. It should be noted that iodine heptafluoride is the one and only molecule belongs to AX7 type interhalogen. The reason for this is that iodine is the biggest reactive halogen and fluorine is the smallest reactive halogen. So, when iodine and fluorine combines together, iodine can extend its valency up to 7, which results in the formation of iodine heptafluoride. Now, we are discussing the detailed structure of iodine heptafluoride. First of all, we have to find out the hybridization of iodine heptafluoride. Iodine is the central atom here with the 7 valence electrons, and you can see the presence of 7 monovalent fluorine atoms around the central atom iodine. And IF7 is having no charge. From this we can arrive at the conclusion that V is equal to 7, that is number of valence electron is equal to 7, number of monovalent atom is equal to 7, cationic charge is 0, anionic charge is 0. On substituting these values in the expression for finding out the hybridization, that is half into V plus A minus A plus A divided by 2, we will get half into 7 plus 7 minus 0 plus 0, that is equal to 7. So there are 7 orbitals that take part in hybridization, and the hybridization scheme is sp3d3 with respect to iodine, the central atom in iodine heptafluoride. Now we can illustrate the hybridization by looking onto the electronic structure of the central atom iodine. Thus we arrived already at the conclusion that in IF7 molecule, the central atom iodine shows sp3d3 hybridization. Now the question arises, how we can explain the sp3d3 hybridization of the central atom iodine in iodine heptafluoride? For this, I am taking the ground state and excited state electronic configurations of the central atom iodine. It should be noted that the central atom iodine has an outer electronic configuration in the ground state as 5s2, 5p5 and 5d0. Whenever I am representing it in box-wise notation, this is the 5s orbital with the 2 electron. This is the 5p orbitals, 5px, 5py and 5pz with the 5 electrons. I can mark it like this, 1, 2, 3, 4 and 5. So 5 electrons are present in 5p. And this 5d orbitals, there are 5d orbitals, and among these 5d orbitals, there will be no electrons present in the ground state. So this will be the ground state electronic arrangement of iodine in iodine heptafluoride. And what happens in the excited state? So now I am representing iodine in the excited state. In the excited state, it should be noted that the electrons which are already paired, that is paired electrons shown in present in 5p orbitals are excited to the 5d. So this electron is excited, this electron is also excited to 5d, and there is one more 5s which is already paired, that electron is also excited to 5d. So in the excited state arrangement, iodine can be represented like this. 5s, this is the 5s orbital with 1 electron, because other electron is already promoted to the 5d. So this is the 5p orbitals arrangement, 5p 1, 2 and 3. This is because these 2 electrons which are already paired shifted or excited to the 5d. And now in 5d orbitals there are 3 unpaired electrons, 1, 2, 3. 3 unpaired electrons are there. So this is 5s, this is 5p and this is 5d. All these half-filled orbitals, namely 1s orbital, 3p orbital and 3d orbital, undergo a hybridization scheme. That hybridization is nothing but sp3 and d3. So this is the explanation of sp3d3 hybridization in IF7 molecule, the central atom iodine. Now, with respect to the structure of IF7, it is very well clear that hybridization leads it to geometry. From the geometry, you can find out the structure of the molecule by ignoring the lone pair of electron. The structure of IF7 is here. The structure is pentagonal bipyramidal. The geometry is the same as the structure. This is because there is no lone pair of electron in the central atom. That is, based on the hybridization and VSEPR theory, the geometry is predicted as pentagonal bipyramidal. The geometry is the same as structure. This is because there is no lone pair of electron on the central atom iodine. The structure and geometry are the same. Both are pentagonal bipyramidal. That is, iodine heptafluoride depicts pentagonal bipyramidal geometry as well as pentagonal bipyramidal shape. Moving on to the bond angle of this molecule, it is clear that the in-plane bond angle is equal to 72 degree and the out-of-plane bond angle, that is equal to 90 degree. That is the representation of iodine heptafluoride by using ball and stick model. That all about the structure of iodine heptafluoride. Now we are discussing the structure of ClF3. This is another type of interhalogen which belongs to the category AX3. It is a representative example of AX3 type interhalogen. In ClF3 molecule, chlorine being the bigger atom and it is taken as the central atom, and you can see 3 surrounding fluorine atoms are also here in ClF3. We are now moving into structural details of chlorine trifluoride, out of which we are finding out the hybridization first. Chlorine is the central atom. It is associated with the 7 valence electrons and 3 monovalent fluorine atoms around the central atom. So, ClF3 is also having no charge. Thus, we can conclude that number of valence electrons is equal to 7, number of monovalent atom M is equal to 3, cationic charge is equal to 0 and anionic charge is equal to 0 since this molecule is neutral. So, you can substitute these values in the expression for finding out the hybridization from molecular formula, that is half into V plus or minus C plus A. On substitution, we will get half into 7 plus 3 minus 0 plus 0, that is equal to 5. That means 5 orbitals are take part in hybridization. So, it is clear that the hybridization is sp3d hybridization. So, the molecule ClF3, the central atom chlorine depict sp3d hybridization. Now, we can illustrate the hybridization scheme in ClF3 by taking the electronic configuration of the central atom chlorine. Prior to that, we conclude already that in ClF3 molecule, the central atom chlorine shows sp3d hybridization. Now, I am taking the electronic structure to illustrate the sp3d hybridization in ClF3. We know that chlorine is the central atom. Now, I am representing the ground state electronic arrangement of chlorine atom. The outer shell configuration will be 3s2, 3p5 and 3d0. This will be the ground state electronic arrangement of chlorine atom, and whenever it is represented in box-wise notation, this is the 3s orbital. So, 2 electrons are there. There are 3 p orbitals, namely px, py and z. There are total of 5 electrons there, 1, 2, 3, 4 and 5. This is electronic arrangement in 3p subshell, and another case is the 3d. There are no electrons present in 3d subshell. So, 3d0 will be the arrangement. So, in the ClF3 molecule, the central atom chlorine in ground state has this electronic arrangement, that is 3s2, 3p5 and 3d0. Now, let us think what is going on when electrons undergo excitation. So, chlorine in the electronic excited state or chlorine in the excited state, there will be some changes occur during this, and for the formation of ClF3 molecule, we require 3 half-filled orbitals. So, for that, one of the electron present in the 3p is get promoted to 3d. So, we can represent the excited state electronic arrangement like this. This is 3s. There is no change. 2 electrons are present as such. Now, I am taking the 3p subshell. One of the electron from here is promoted to 3d. So, I can represent this arrangement. This is 3d previously. There are 5d orbitals. So, this is 3d. And this is 3p. One electron from 3p is promoted now to 3d. So, there are 3 half-filled orbitals and 2 completely filled orbitals. All these orbitals with the electrons undergo hybridization. That hybridization is 1s, 3p and 1d. So, the hybridization is nothing but sp3d hybridization. In sp3d hybridized orbitals, there are total of 5 sp3d hybrid orbitals. 2 are occupied by lone pairs and 3 of them are half-filled. These half-filled 3 sp3d hybrid orbitals overlap with the half-filled 2p-z orbital of fluorine to form the ClF3 molecule. Based on the hybridization and VSEPR theory, the geometry of the molecule can be predicted as trigonal bipyramidal. But from the previously discussed electronic arrangement, it is very well clear that the central atom chlorine has 2 lone pair of electron. Therefore, in the trigonal bipyramidal geometry, there are 2 lone pairs of electron which are occupied in the planar position. That's why 2 lone pairs are also shown in the trigonal bipyramidal arrangement. I am simply representing that trigonal bipyramidal geometry with the 2 lone pairs like this. Here there is a central atom chlorine and 2 lone pairs are present on the central atom chlorine. Here there is a bond pair. These are at the 3 corners of a triangle. These are at the 3 corners of a triangle. And 2 more bond pairs has to be arranged. They are present at the axial position. So, one fluorine is here, another fluorine is here. This about trigonal bipyramidal geometry of ClF3. Here you can clearly see the position of 2 lone pairs which are at the triangle position. So, this about the trigonal bipyramidal geometry of the ClF3 molecule. Now, moving on to the structure. Since there is 2 lone pair, the shape or structure is different from geometry. And it is clear that the geometry is different from the shape or structure. and hence if you are ignoring the contribution from the lone pair, we will get the shape of ClF3 molecule. It is clear that whenever you are ignoring these two lone pair, you will arrive at a shape, and this shape is called the T shape. So, the ClF3 molecule has a structure of T, or ClF3 molecule shows T shape. Discussing another interhalogen, that is BRF5. From the molecular formula itself, it is clear that this BRF5 is a AX5 type interhalogen. Here the central atom being the bromine, which is the biggest in size when compared with the 5 fluorine atoms. So, BRF5 molecule is a AX5 type interhalogen, and now we are discussing the structural details of BRF5. First of all, we are looking on to the hybridization of BRF5 molecule. Bromine is the central atom with the 7 valence electrons, and 5 monovalent fluorine atoms are present around the central atom. It should be noted that from the molecular formula, you cannot see any charge. That's why we can say that BRF5 is having no charge, or it is a neutral molecule. Thus, we can say number of valence electrons V is equal to 7, number of monovalent atoms around the central atom is equal to 5, cationic charge is equal to 0, anionic charge A is equal to 0. On substituting this in the expression for finding out the hybridization, that is half into V plus A minus E plus A, we will get this value, that is half into 7 plus 5 minus 0 plus 0. You are getting a value equal to 6, and this is equal to sp3d2 hybridization. The value of 6 corresponds to sp3d2 hybridization. This is because 6 orbitals are take part in sp3d2 hybridization. So, we proved that in BRF5 molecule, the central atom bromine shows sp3d2 hybridization. This sp3d2 hybridization in BRF5 molecule can be illustrated by taking electronic arrangement of the central atom bromine in BRF5. Now, we are trying to explain the hybridization scheme of bromine in BRF5 with respect to electronic arrangement of bromine in the ground state as well as in the excited state. First of all, bromine in the ground state. Bromine has an outer electronic configuration of 4s2, 4p5 and 4d0. Whenever it is represented by using box-wise notation, this is 4s with the 2 electron, this is 4p subshell with the 5 electron, 1, 2, 3, 4 and 5, and this is 4d subshell, they are total 5 in number, 4d subshell with the no electrons. Now, let us think what is happening during the excitation of electron. That is, bromine in the excited state has some electronic arrangement which is new when compared with the ground state electronic arrangement. During the formation of BRF5, we require 5 half-filled orbitals, because half-filled orbitals on overlap produces bonds. In BRF5, there are 5 bromine-fluorine bonds. Therefore, we must have 5 unpaired electrons at least during excitation. In the ground state, there is only 1 unpaired electron. So, in the excited state, we must get 5 unpaired electron to ensure the formation of BRF5. For that purpose, electrons from 4p is promoted to 4d. Another paired electron is also promoted to 4d. So, the new electronic arrangement will be like this. There is no change in 4s orbital. This is 4s as such. Now, I am representing electronic arrangement of 4p. 2 paired electrons get promoted to 4d. So, the new arrangement in 4p is 4p3, and 2 electrons are present in 4d. Therefore, the electronic arrangement is like this. This is the electronic arrangement in 4D. Now you are having 5 half-filled orbitals and 1 completely filled orbitals. All these undergo hybridization, and the hybridization scheme will be 1s, 3p and 2d. So the hybridization scheme is sp3d2 hybridization. As a result of the sp3d2 hybridization, there will be 6 sp3d2 hybrid orbitals, out of which 5 are half-filled. These 5 half-filled sp3d hybrid orbitals overlap with the 2p-z orbital of fluorine to generate BrFi molecule, and 1 hybrid orbital is completely filled with a lone pair of electron. So it is clear that in the structure, in the geometry of BrFi molecule, there will be a lone pair of electron in the central atom bromine. Now, based on the hybridization and VSEPR theory, the geometry can be predicted as octahedral, and this is the octahedral geometry. Here you can clearly see the position of the lone pair, which is at any one corner of the octahedron, and in order to specify the shape, we have to ignore the contribution from the lone pair. Since there is a lone pair present in the central atom bromine, the geometry is different from shape, and we are now getting the shape by removing the lone pair of electron. Since there is one lone pair on the central atom bromine, the shape and geometry of BrFi are different, and this is the representation of the geometry as well as the shape. Here there is a lone pair, so this is octahedral with the one position occupied by lone pair, and if you cut or remove that lone pair, we will get the shape. Shape is always rigid, or structure is always rigid, and you can say that the structure of this molecule is square pyramidal. That is, shape or structure of the molecule is obtained by excluding the lone pair, and hence BrFi has square pyramidal shape or square pyramidal structure. Now we are discussing some selected sulphur fluorides. First of all, we are taking the structure of sulphur tetrafluoride. As the name indicates, this is a tetrafluorine compound of sulphur with the central atom sulphur. Sulphur is bigger in size and small in number, so it can be considered as the central atom. And here there are 4 fluorine atoms. In order to establish the structure of SF4 molecule, we have to first overlook into hybridization of SF4 molecule. Sulphur is the central atom. Since it belongs to oxygen family, it has 6 valence electrons, and you can see from the molecular formula that there are 4 monovalent fluorine atoms around the central atom sulphur. SF4 as such is having no charge, therefore we can arrive at these values. V, that is nothing but number of valence electron, that is equal to 6. Number of monovalent atoms equal to 4. Cationic charge is 0, anionic charge is 0. Therefore, on substituting in the expression for hybridization, we will get hybridization equal to 5, that is nothing but 5 orbitals are take parting, and the hybridization will be sp3d hybridization. Thus, in SF4 molecule, the central atom sulphur shows sp3d hybridization. Now we are going to illustrate the sp3d hybridization of sulphur in SF4 molecule by considering the electronic structure. First of all, I am representing the electronic structure of sulphur atom in the ground state. In the ground state, the sulphur atom has an electronic arrangement of 3s2, 3p4 and 3d0. I am simply representing it in the box-wise notation 3s2, you can see, and the next case is a 3p with the 4 electrons arranged like this. This is 3p4 arrangement, and there are no electrons present in the 3d subshell. So this is the 3d arrangement. Now let us think what is going on when electrons excited in the sulphur atom, or electronic excitation happens in the sulphur atom, leads to a new electronic configuration. It should be noted that here as such only 2 half-filled orbital, but for the formation of the SF4 molecule we require at least 4 half-filled orbitals. For that, in the excited state or during excitation, the paired electron from the 3p subshell get promoted to 3d. So the new electronic arrangement is like this. This is 3d, there is no change, and in the case of 3p, 1 paired electron will get promoted to 3d. So this is now exactly half-filled. 3p orbitals are half-filled. This is 3p orbitals, and 1 electron just entered into one electron just entered into the 3D. So, this is the 3D arrangement, and these orbitals with the electrons now undergo mixing up, and the mixing up is between 1s orbital, 3p orbital and 1d orbital. So, the hybridization scheme is nothing but sp3d hybridization. As a result of sp3d hybridization, we will get a geometry. The geometry is nothing but a trigonal bipyramidal geometry. You can clearly see the position of a lone pair here. The lone pair is at the trigonal planar position of trigonal bipyramidal geometry. So, this is the geometry of SO4 molecule which we arrived from the hybridization. Now, in order to get the structure, we have to think about lone pairs. Since there is one lone pair on the central atom sulphur, the shape and geometry of SO4 are different. That is, in order to get the shape, I have to exclude the lone pair. This is trigonal bipyramidal geometry with one lone pair. If I remove that lone pair, I will get a new shape, and that new shape is called the seesaw shape. That is, the shape of the molecule is obtained by excluding lone pair, and hence SO4 molecule shows a seesaw shape, or the structure of SO4 is seesaw. Now we are discussing another sulphur fluoride, that is sulphur hexafluoride. It should be noted that in sulphur hexafluoride, the central atom sulphur has a covalency of 6. 6 is the maximum covalency of the central atom sulphur that is utilized during the formation of S of 6. Previously, we discussed a molecule that is S of 4, where the covalency of the central atom sulphur is only 4. However, in S of 6, the central atom sulphur exhibit a covalency, a maximum covalency of 6. Now we are entering into more details about the structure of S of 6. First of all, we are focusing on the hybridization of the central atom sulphur in S of 6. It is very well clear that the sulphur is a central atom with the 6 valence electrons, and you can see 6 monovalent fluorine atoms from the molecular formula around the central atom sulphur. SF6 is a molecule without any charge. So, it is a neutral molecule, or SF6 is having no charge. This leads to the conclusion that the number of valence electron V is equal to 6 around the central atom. Number of monovalent atoms is also 6. Cationic charge as well as anionic charge will be equal to 0. You can substitute these values in the expression for finding out the hybridization from molecular formula to get the hybridization as 6. That is, 6 orbitals are take part in hybridization. That hybridization is nothing but sp3d2 hybridization. Thus, we can arrive at the conclusion that in SF6 molecule, the central atom sulphur shows sp3d2 hybridization. This hybridization can again be proved by looking onto the electronic structure of the central atom sulphur. It is very well clear that the central atom sulphur in the ground state has an electronic configuration of 3s2, 3p4 and 3d0. This can be represented like this. This is 3p2. These are 3 p orbitals which give a 3p4 arrangement like this, and there are no electrons present in the 3d subshell, so 3d0. Sulphur in excited state shows some electronic excitations to meet the generation of S of 6. In order to form S of 6, the central atom sulphur have 6 half-filled atomic orbitals. But in the ground state, you can see there are only 2 half-filled orbitals. So, these paired electrons excited to the D, and this paired electron from the 3 is also excited to 3D, and as a result the electronic structure in excited state can be represented like this: 3s1, 3p3 and finally 3d2 will be the electronic arrangement like this. So, this is 3s, this is 3p and this is 3d. The orbitals with the electrons undergo hybridization, and the hybridization scheme will be 1s, 3p and 2d orbitals are participating in the hybridization, and the hybridization is nothing but sp3d2 hybridization. It is very well clear from the electronic structure that all sp3d2 hybrid orbitals are half-filled. These 6 sp3d2 hybrid orbitals overlap with the half-filled 2p-z orbital of fluorine to form 6 SF bonds, which enable the formation of SF6 molecule. From this electronic arrangement, you can see there will be no electron pairs or lone pairs present in the center atom sulphur. Thus, based on hybridization and geometry, VSCPR theory, it is clear that the geometry of the molecule will be octahedral, and since there is no lone pair of electron on the central atom, we can say that the geometry is the same as shape, or geometry is the same as structure, and hence the structure of SF6 molecule is also octahedral. Now we can have some problems based on the concept we have learned. This is the first MCQ. The central atom in XeF2 has, these are the options, sp2 hybridization and sp3 hybridization and trigonal bipyramidal geometry, sp3d hybridization and linear shape, sp3d2 hybridization and square planar shape, sp3d hybridization and bent shape. From the molecular formula, you can arrive at hybridization. From hybridization, you can arrive at geometry. From geometry, if you are ignoring the lone pair, you will arrive at the shape. Based on this concept, you can arrive at the final answer as option B, that is sp3d hybridization and linear shape. Now moving on to another MCQ. The bond angle in ClO2 minus is approximately. These are the values: 120 degree, 109.5 degree, 111 degree and 105 degree. From the molecular formula, you can arrive at the hybridization. The hybridization will be sp3, and we are anticipating a bond angle of 109.5 degree. But owing to the presence of the electron pair repulsion, the bond angle is slightly higher than 109.5 degree, and the correct answer is option C, that is 111 degree. Now we are entering into next MCQ. The interhalogen compound ClF5 has which type of hybridization and shape? These are the options: sp3d2 hybridization square pyramidal shape, sp3d2 hybridization octahedral shape, sp3d hybridization seesaw shape, and finally sp3 hybridization with the trigonal pyramidal shape. On careful analysis of hybridization geometry and shape, you can arrive at the final answer as option A, sp3d2 hybridization, but the shape is square pyramidal, similar to BRF5. Now another MCQ. Which of the following compounds has the same shape as PCl5? These are the options: SF4, IF5, SbCl5 and ClF3. It should be noted that Sb or antimony is an element that belongs to same phosphorus family or nitrogen family. So SbCl5 is having similar shape as that of PCl5. So your answer is option C, SbCl5. This is the last MCQ of this unit. The shape of triiodide anion is, these are the options: bent, linear, trigonal bipyramidal and trigonal planar. On careful analysis of the molecular formula and on evaluating the hybridization and geometry and the shape, you can arrive at the conclusion that this I3 minus anion is a linear shaped species. Here there is a central atom iodine and 2 iodine atoms are arranged at the axial position. There are 3 lone pairs. Excluding the lone pair, you will get a linear shape. That's all about the present module. Have a nice learning experience. Thank you.